Welcome back. This is Fundamentals of Micro and Nano Fabrication. My name is Sushoban Awasthi from IFC Bangalore, and today we shall discuss some of the advanced concepts of diffusion which is under the general module of additive processing. So, till now we have only discussed how to use diffusion to create a doped layer at the surface of a semiconductor wafer. However, blanket diffusion is typically not useful. If you want to make a device, you always have to pattern it. You want to have dopants under selective regions. So, this is what I am trying to explain here. So, what you want is you want to say you start with n-type silicon, then you grow some oxide, and then you want certain dopings to occur on the either side of this oxide, but not below the oxide. If you want to do that with diffusion, then you need to figure out a method to prevent diffusion from happening in this oxide region. So, one advantage is that the oxide can act as a barrier. The oxide is amorphous material, probably the diffusion through that material is very slow, but then what oxide thickness is enough for the material to prevent diffusion of the material through it? Like, so is 5 nanometers enough? Is 100 micron enough? What thickness is required? In order to do that, we need to understand the concept of masking. So, that is what is called masking. Typically, we want some material that can prevent the diffusion of the material of the element that you are diffusing, and then you put that mask on before diffusion, do the diffusion process, but after the diffusion process you only get the dopant in the region where the mask was not there. Common masks are silicon nitride and silicon dioxide. The point to remember is the mask must be non-contaminating, because remember, contamination will grow faster than dopant inside your material, so the mask has to be non-contaminating. There must be a way to remove the mask later so that it does not mess up your flow, and then you also need to know what thickness, right. So, the easiest way to answer that question is just look at the diffusion coefficient of the element in that mask. So, this is not the d of these elements inside silicon, but the d of these elements inside silicon dioxide, right, the oxide. So, let us look at the typical numbers. So, boron is around minus 17 to minus 14. If you remember the order of magnitude numbers for diffusion of boron in silicon, these are lower. Similarly, for phosphorus, the diffusion of phosphorus is lower in silicon dioxide than it is in silicon. Same with antimony, same with arsenic. The one notable exception is gallium. The diffusion of gallium is very fast through the oxide for reasons that are beyond this course. And this is actually one of the reasons why gallium is not very popular as a p-type dopant in silicon. It just goes through the oxide too fast, and that means it is very hard to mask it. Now, what is the thickness we need? To a first order, we know that the thickness of a diffusion layer is under root dt. So, if we know in order to know the thickness that will prevent diffusion, that must be less than or equal to a few multiples of dt, under root dt. Right. So, here is that mathematics. So, most diffusion processes tend to last something in between 1 minute to 30 minutes or 1 hour. So, that is your time. The d you already know from the last table. So, the amount of thickness you need is given by simply that formula under root d tau, and which is what is plotted here. So, for most cases where the diffusion times are 15-30 minutes, around 100 to 200 nanometers of silicon dioxide is enough to storm any dopant except gallium. Gallium is not stopped by silicon dioxide. So, the other advanced concept I like to introduce is the concept of a two-step diffusion. The basic idea behind this is that typically diffusion processes are very hard to control. We solved two cases of Fick's equation, one was at finite source and one was at infinite source. Any practical diffusion is probably somewhere in the middle, but the exact mathematical profile is hard to model and even harder to reproducibly do. So, while diffusion is a very easy process to do, getting it repeatably the same in every wafer day in day out is very tricky. To solve this problem, people often use a two-step process, where the deposition of the dopant at the surface and the diffusion of the dopants inside silicon is sort of split into two halves, instead of doing it all in one shot. So, there is a pre-dep step or a pre-deposition step and a drive-in step. Okay. So, during the pre-deposition, which is often at low temperature, you deposit a dopant source on the surface. So, supposing you are starting with POCl3, during the pre-deposition step you will form the phosphorus oxide or phosphosilicate glass at the surface. So, that is happening in the pre-deposition. Then you would take the same material, so you form a dopant oxide on top of your silicon. Because this dopant oxide is in contact with silicon, some amount of dopant would diffuse even at this low temperature, given by the solid solubility and other considerations. So, you would form a very thin layer of doped silicon at the surface. Next, you would take this wafer and do a dry-in step. A dry-in step typically is under oxygen and at higher temperature. So, during this step, you would not just diffuse the doped silicon further inside silicon, which is what I am trying to show here, but you would also form a layer of silicon dioxide. Now, this silicon dioxide, as we have just discussed, is a masking layer. It does not allow diffusion of dopants any further. So, this silicon dioxide will now isolate the dopant oxide that you had formed on the top from the silicon below. So, anything that has gone through in the pre-dep step will go through, will continue to diffuse further, but fresh dopants will not be able to make its way from the dopant oxide into the silicon. Now, if you use your analysis, you would see that the pre-dep step is sort of an infinite source diffusion problem, where you have a lot of dopant on the top and a very little amount of diffusion is occurring. And on the right, you have effectively a finite source problem, where there is a fixed amount of dopant that has already diffused through, and now that dopant will go in further, but extra dopants cannot make their way from the top into the silicon. So, now just playing with the temperature and the diffusivities of these temperature and hence the diffusivities of these two steps, you can actually create an arbitrary recipe. You can actually make a recipe that is completely infinite source, or you can have a recipe that is completely finite source, or anything in the middle. This is a common recipe that we actually use at ISC to get I think p-type dopants. So, we do a pre-deposition of phosphorus silicate glass at 800-900 degrees C for 10 minutes or so in oxygen and ambient. This deposits the phosphosilicate glass, and this is right now in the infinite source regime, and then we do a dry-in at around 900 to 1000 degrees C for around 10 to 30 minutes, depending upon how deep we want the dopant to be, and this is typically a finite source regime operation. Overall, these two processes are much more repeatable and controllable than a simple diffusion process would be. Another advanced concept to know, which is important, is interstitiality diffusion. Till now, we have only introduced two diffusion mechanisms. One was substitutional, one was interstitial. This is a mixture of the two. What this needs is a silicon interstitial. So, the mechanism starts with the silicon interstitial interacting with a substitutional impurity and exchanging its position. This substitutional impurity is now an interstitial impurity, which again interacts with another silicon substitutional silicon, thereby creating a new silicon interstitial and puts itself in a new substitutional position. Effectively, what has happened is you started with a silicon interstitial, you have ended with a silicon interstitial. So, the concentration of interstitial has not changed, but the position of the impurity atom has. And using this process, a lot of impurities that are substitutional can actually go through the material much faster than their substitutional diffusion mechanisms would suggest. Because remember, in order for this impurity to move by substitutional mechanism alone, it must need a silicon vacancy, which is harder to come by. But in this process, by using a silicon interstitial, it can move via an interstitial mechanism, which tends to be faster. So, this sort of a mixed or hybrid diffusion is sort of very important for impurities such as boron and phosphorus, and in fact, you cannot model their doping profiles accurately without accounting for this mechanism. This is just one of the possible complicated mechanisms. Actually, those who look into the matter in detail can tell you way more complicated mechanisms, but for the purpose of this course, this is enough. So, a few consequences of this is that reality of diffusion is a little more complicated than the simple Frick's model or a simple substitutional or interstitial model would suggest. The second thing to remember is diffusion of impurities is affected by silicon interstitials and silicon vacancies. This is slightly non-intuitive. Why should presence or absence of silicon vacancy or interstitial affect impurity? But it does, because the mechanism depends upon it, right? Both interstitiality and substitutional mechanisms require the presence of a vacancy or interstitial. And we all know that the vacancy interstitial concentration changes with temperature. So the diffusion coefficients of these mechanisms also change with temperature because of those changes. Furthermore, any other process that creates substitutionals or interstitials on its own, for example, as we will see, oxidation or nitridation creates these, would also enhance the diffusion. So this is a second order effect. So even though you would not expect oxidation to make any changes in the diffusion profile, it would, because it would create more vacancies and interstitials and increase your diffusion. So the practical example I can show you to explain this process is given on the right. So supposing you through a diffusion mechanism you created a doped layer, all great, good. After that you deposited some silicon nitride as a masking layer, and then you started oxidizing your wafer. Okay. Now this process does happen in the middle of fabricating a CMOS transistor in silicon. So as you are oxidizing this doped layer, you are actually creating substitutionals and interstitials, and those will cause the diffusion to enhance. So of course, because you are doing this at high temperature, you do expect the dopant layer to become thicker everywhere. So everywhere this dopant layer will become thicker, but it will be especially thicker right underneath the area where the oxide is being formed. So it will be especially thick here, and that is something you would not expect unless you understand the mechanism by which the diffusion is occurring, right. So there is an enhanced diffusion here simply because of vacancies and interstitials. This is just a table to show you what sort of defects, silicon defects are created while doing certain processing. Implantations creates both vacancies and interstitials, oxidation creates interstitials, and nitridation creates vacancies. Overall, this is just a table for what sort of complicated mechanisms can exist for a given dopant. So boron and phosphorus, all of these you expect substitutional. So all of them do substitutional, but they also do something else. So for example, boron almost always does interstitiality. Like even though you would expect it should do substitutional, because it is so small, it invariably always does interstitiality, simply because its misfit ratio is so small. So boron always diffuses faster. And point of note, when you are doing oxidation, boron will diffuse even faster, because oxidation always creates interstitials. Phosphorus tends to do both interstitial and substitutional. So around 20 to 60% is substitutional or vacancy dependent, and around 80 to 40% is interstitiality or interstitial dependent. So it is somewhere in the middle. The other extreme case is arsenic. In arsenic, the misfit ratio is 1, which basically makes it extremely ideal. It almost always does substitutional only. Antimony is absolute extreme, where it does not do interstitiality at all. It is way too big for it, so it does not form silicon interstitial. It does not form interstitials in silicon, so it cannot do interstitiality diffusion. And each of these mechanisms then has the consequence. For example, this mismatch causes strain, which causes dislocations and which reduces diffusion. At the same time, oxidation enhances diffusion. Oxidation also enhances the diffusion of phosphorus. However, oxidation does not enhance significantly the diffusion of arsenic or antimony. Another advanced concept of diffusion is to understand that diffusion is not concentration independent. For easy math, we assumed that D is independent of C and made the second law of Fick's very easy to solve, but D is not constant. D does depend upon concentration because of complicated mechanisms that we have not discussed here, and if that happens, you have to account for it in order to model your profile accurately. Just to get an intuition, all what really happens is that diffusion is faster in areas of higher doping than otherwise, right? So diffusion is enhanced. That is what effectively happens. So if because of your error function or because of Gaussian profile you were expecting this blue line, because of diffusion is concentration dependent, you will have higher diffusion in areas of higher concentration. So, you would essentially get red line. So, the red line you will have more diffusion in the area of higher concentration than area of lower concentration. So, your profile tends to be squarer than you expect. So, instead of this slightly more blunt blue curve, you would get a sharper red curve. There is also field enhanced diffusion. So, boron would form a boron minus impurity and a hole, which is the positive charge. And at high temperatures, or rather at any temperature, the diffusion of the boron minus, this is the substitutional impurity, and the hole, which is just a charge, are different. So, there is no reason to assume that they will both diffuse at the same rate. The hole tends to diffuse faster. So, the hole will show a profile that looks like the orange, and the boron minus will diffuse slower. So, that will have a profile that looks like blue. What that means is there is a certain portion of your diffusing layer which is negatively charged and a certain portion of your diffusing layer that is positively charged, and of course, positive and negative charges will create an electric field, and this electric field will then affect the diffusion of the negative charge, which is the boron. Since the electric field is in this direction, it will actually push the boron minus faster, right? It will attract it towards the positive side, which basically means the boron minus will feel an enhanced diffusion. It will feel an attractive force that will increase its diffusion. How much will it enhance depends upon the mathematics that looks like this. It really depends upon what concentration of holes do you have and what temperature you are at. If you look at this formula, Ni is what is accounting for the charge, and typically Ni values are very low at room temperature. However, at high temperature the values of Ni's can be significantly higher, and that is why at high temperature you must account for them. So, for example, at high values the Ni values can be 10 power 18 and on. So, for cases where the dopant is more than 10 to the power 18, you must expect dopant enhanced diffusion, field enhanced diffusion. If your doping levels are less than 10 power 18, this formula tells you you should not expect field enhanced diffusion. So, here is an example of a field enhanced diffusion. This is a profile. So, you would expect the profile, this is a p-type material. So, you started with the p-type wafer and then you diffused an n-type material in it. But because of field enhanced diffusion, you actually changed your profile. So, first thing is that the boron profile that was flat initially, because you started with the boron wafer, so it was flat initially, now has a certain shape. And why did this shape happen? This shape happened because the boron atoms felt a electric field, and also the phosphorus that you were trying to diffuse, the n-type, also got enhanced. So, these kind of things can also happen that will change the profile and give you a slightly different profile than what you expected. This is just a very small subset of various diffusion effects we know. As you would have noticed, silicon is a very well studied material. The diffusion in silicon has been studied to death. People know virtually everything there is to know about it. Here is a list of other type of diffusion that I am not covering in this course and you would not be quizzed upon. The point I am trying to make is, if you are really interested in diffusion as a topic, you may want to read upon these on your own. But by and large, we have models for this. So, in the modern day, we do not rely on hand calculations to accurately predict what our dopant profile is going to look like. In general, you would put this all in a simulator. The simulator has all these models already built in. It would do the math, it would do all the calculations, and as long as your simulations are correct or correctly set up, you would get a very accurate profile, Finally, some characterization methods. So, how do you characterize the dopant, the profile that you have made inside the material? So, the simplest thing you can do is measure resistivity. So, because you have added dopants, you have changed the resistivity of the surface. So, all you have to do is measure the resistivity of the surface. This is most easily done using a 4-point probe method. I will not go into details, but 4-point probe method simply pushes some current, measures voltage, and through a very simple formula tells you what is the sheet resistance, right. However, one thing to note in this is, in order for this to work, you must know the thickness, and that thickness is often unknown because you do not know how deep your dopants have diffused. So, for that often people use SIMS. Once you know resistivity, however, then you can back calculate the doping by the simple graph. So, if you measure a resistivity of 10, you just go up, look up whether you have p-type material or n-type material, and then that gives you a dopant concentration. Now, I mentioned the word SIMS. What is SIMS? So, SIMS is secondary ion mass spectroscopy. It is an advanced technique to actually profile the dopants inside your silicon. So, very simply what it does, it showers the silicon surface with a heavy ion, which causes sputtering on the silicon surface. So, if you remember sputtering, you basically it is a mechanical process. There is a stream of particles that hit the silicon surface and etch the silicon surface, and these silicon atoms that are etched off come off as vapor into the plasma. Those are analyzed by a mass spectrometer, which tells you their mass, and from their mass you can back calculate what element came out. So, if your silicon surface has phosphorus, in the sputtering plasma you will measure silicon signal because you are sputtering silicon, but you will also measure phosphorus signal because you are measuring phosphorus, and you just do this with respect to time. You know how deep you have etched, so you can convert the time axis of etching into a depth axis. So, you would get these figures where you know the concentration of phosphorus as a function of depth. So, this is what SIMS is. It is one of the workhorses to know dopant profiles if diffusion is your work of interest. Finally, I jumped this slide. The old school method of figuring out junction depth was slightly different. People would use selective etching to ink or sort of stain your doped areas and then use microscopy to measure it. I have personally never done this process before. I think it is outdated. I do not know of any setup that exists that actually does this process anymore. So, other than for academic interest, there is no need to understand it, but the concept is fairly cool. So, I will just go through it. So, what you do is you start with a substrate. You have a dope layer on top. Using a grinding wheel, you grind a cylindrical edge into the surface, and then you do some selective etching such that the undoped regions get etched, but the doped regions do not get etched. Okay, and then you go and look at it under a microscope. So, what you would see is, looking from the top, is you would see you would see a component of this thickness. Looking from the top. So, what you would see some strips, but the thickness of those strips can be geometrically related to the depth. So, using some simple geometry, they could actually back calculate what is the depth xj of this layer and give you doping thickness. So, I think the idea is really cool, but yeah, as I said, practically of limited use today. If you want to do this experiment, you just do SIMS. So, with that we come to the end of this lecture. This takes care of the first set of lectures on additive processing, where we discussed diffusion. Next we will look at the more modern technique called implantation and move on from there. Thank you.